Right now, you are screaming through the void, not just spinning on a ball of rock, but racing around a supermassive black hole at 500,000 miles per hour, carried by a star that is itself a tiny spark in a massive cosmic city of 400 billion suns. You live on a speck of dust, and that speck is on an epic, unseen journey. We call that city the Milky Way. And tonight, we are going to leave our front door behind. We are going to travel from the quiet, protected bubble of space where our solar system drifts, past stellar nurseries birthing new suns, through the graveyards of dead stars, and across the massive spiral arms that define our galaxy. We will end our voyage at the very edge of a monster, a supermassive black hole that sits at the galactic center, a point of no return where gravity breaks the laws of physics. If you are ready to see where you really live, to understand the scale of the journey you are on right now, then stay with me. This is the journey around the Milky Way. We begin on Earth, but do not think for a second that we are stationary. You are currently moving at over 1,000 miles per hour just from the planet's spin. That is merely the first layer of your velocity. Earth is also orbiting the Sun at 67,000 miles per hour. That is the second layer. Most people stop there, satisfied that they understand their place in the cosmos. But the Sun itself is the real engine of this journey. The Sun is dragging us, along with every planet, comet, and asteroid in the system, around the center of the Milky Way at a staggering 14,000 miles per hour. Every single second, you travel 140 miles through the galaxy. You do not feel it because everything around you is moving together. There is no wind, no friction, no sensation of speed. You are a passenger on a starship that is moving faster than any bullet, faster than any human machine, faster than anything you can intuitively understand. But the path is not a simple circle. It is a wave. As the Sun orbits the galactic center, it bobs up and down through the flat disk of the galaxy, like a car hitting a rumble strip on a highway. It takes the solar system about 230 million years to complete one full lap. We call this a galactic year. The last time Earth was at this exact point in its orbit across the galaxy, the supercontinent Pangaea was just beginning to break apart, and the first dinosaurs were only starting to walk the Earth. This bobbing motion is critical. Every 30 to 40 million years, we pass through the densest part of the galactic disk. Some scientists believe this period correlates with mass extinctions on Earth. When we hit that dense plane, we are exposed to increased cosmic radiation and gravitational chaos from passing stars and gas clouds. It is like driving through a dangerous neighborhood. Right now, we are in a quiet suburb. But that is not the whole story. You see, our solar system is not floating in empty space. We are inside a ghost, a cavern. Astronomers call it the local bubble. This is a massive, hollowed-out region of space that stretches for over 1,000 light-years in every direction. We are inside a cosmic cathedral carved by violence. About 10 to 20 million years ago, a cluster of massive stars in this region reached the end of their lives. When a star 8 times heavier than our Sun dies, it does not go quietly. It explodes as a supernova, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. These explosions happened again and again. Star after star detonated, creating a shockwave that swept away the surrounding gas and dust like a cosmic broom. The result is the local bubble, a warm, thin pocket of space filled with gas, heated to millions of degrees. We are living inside the aftermath of ancient stellar violence. This bubble acts as a shield. It deflects the dense, cold clouds of gas that would otherwise bombard us. Without this protective shell, the Earth might look very different, and life may have struggled to take hold. As you look up at the night sky, the stars you see are mostly the ones on the far side of this bubble, shining through its walls. The Milky Way band you see is the edge of the bubble in every direction. We are like a submarine passing through a deep ocean, protected by a glass hull. But our journey is just beginning. We are not at the center of the local bubble. We are drifting toward one of its walls. In about 5 million years, we will punch through this protective layer and enter a much denser, wilder part of the galaxy. That is where we are heading now. As we leave the safety of the local bubble, we approach the nearest major star-forming region, the Orion Molecular Cloud Complex. It is only 400 light-years away. If your eyes could see infrared light, this region would glow brighter than any star in the sky. This is the factory floor of the galaxy. Here, vast clouds of molecular hydrogen and dust are collapsing under their own gravity, condensing into knots of matter that become new stars. The process is not gentle. When a gas cloud collapses, it does not just turn into a star, it fragments. It breaks into dozens or hundreds of pieces. Each piece becomes a new star. They are born as siblings, crowded together in a tight group called an open cluster. As you watch the Orion Nebula through a telescope, you are seeing a stellar nursery in real time. The 4 bright stars at the center, the trapezium, are massive, hot stars that have just ignited. Their ultraviolet radiation is carving a cavity in the surrounding gas, illuminating the cloud and giving it that beautiful sculpted look. The material in these clouds is the raw stuff of the universe. It is 73% hydrogen, 25% helium, and a tiny fraction of heavier elements. But that tiny fraction is everything to us. The calcium in your bones, the iron in your blood, the oxygen you breathe. None of it existed at the beginning of the universe. It was all forged in the hearts of stars inside clouds, just like this one, billions of years ago. When those stars exploded, they scattered those elements across the galaxy. We are not just looking at star birth. We are looking at our own origin story. Hold on. We need to talk about scale again. The Orion Arm, the spiral feature we live in, is not a major arm. For a long time, astronomers thought it was just a small spur connecting the larger Sagittarius and Perseus arms. But recent observations using radio telescopes have shown that the Orion Arm is much bigger than we thought. It stretches for over 20,000 light-years. It is a major galactic highway. We are not in a backwater. We are part of a significant structure. But as we travel further from our local neighborhood, we must look at the dead. Scattered throughout the Orion Arm, invisible to our eyes, are the remnants of stars that have already lived and died. These are the stellar graveyards. The most common are white dwarfs. They are the cores of dead stars like our sun. A white dwarf packs 60% of the sun's mass into a sphere the size of Earth. A teaspoon of that material would weigh as much as a car. The nearest white dwarf is only 8.6 light-years away. It is called Sirius B, and it is a ghost orbiting a bright star. But the real monsters in the graveyard are the neutron stars. When a star 8 times or more massive than our sun explodes, the core does not just stop. it crushes itself. The gravity is so intense that it forces protons and electrons to merge into neutrons. The entire core, containing more mass than the Sun, is compressed into a sphere only 12 miles across. The density is so high that a sugar cube-sized piece of neutron star would weigh 6 billion tons, more than Mount Everest. Some of these neutron stars spin. They spin hundreds of times per second, shooting beams of radiation from their magnetic poles. We call them pulsars. They are cosmic lighthouses. Their timing is so precise that they rival atomic clocks. The fastest known pulsar spins 716 times every second. If a neutron star were placed where the Moon is, its magnetic field would wipe every credit card on Earth. Getting within 600 miles of one would be instantly fatal. These stellar corpses are not just curiosities, they are laboratories for physics. They help us understand matter under extreme conditions that we could never create on Earth. Now, our journey takes a sharp turn. We are leaving the Orion Arm behind and moving into the massive Perseus Arm. This is one of the galaxy's major spiral arms. It is a cosmic superhighway. While our local arm has modest star formation, the Perseus Arm is where the giants live. Here, stars can be 50 or even 100 times the mass of our Sun. These are the blue-white monsters. They burn so hot and bright that they consume their fuel in just a few million years. The Perseus Arm contains some of the most spectacular objects in the sky. The Eagle Nebula is here, with its famous pillars of creation. Those pillars are towering columns of gas and dust being eroded by the intense radiation from nearby massive stars. The Rosette Nebula is here, glowing a deep red from ionized hydrogen. Traveling through the Perseus Arm would be like driving through a cosmic construction zone mixed with a demolition site. Everywhere you look, stars are being born, and stars are exploding. As we pass through these arms, we encounter stellar cities, star clusters. The most spectacular are the globular clusters. These are ancient spherical collections of hundreds of thousands, sometimes millions of stars. They are the oldest things in our galaxy, over 12 billion years old. They formed when the universe was just a toddler. A globular cluster is so dense that if we lived in the center of one, there would be thousands of stars brighter than Venus in our sky. Night would be a permanent twilight. But our journey through these arms reveals the hidden structure of the galaxy. We are not just seeing stars, we are seeing rivers. Between the stars, there is an invisible ocean of gas and dust. These interstellar currents flow between the spiral arms, carrying the raw material for future stars. They are guided by the galaxy's rotation and magnetic fields. These streams are not empty. They are filled with turbulence. Supernovae inject shock waves. Stellar winds blow bubbles. It is a chaotic ecosystem. The flow of this gas is directional. Much of it is being funneled inward toward the center of the galaxy. We are now following that flow. We are moving into the inner galaxy. The next major structure we hit is the Scutum Centaurus Arm. This is the longest and most massive spiral arm in the Milky Way. It wraps more than halfway around the entire galaxy. This is the industrial heartland of the Milky Way. The star formation rate here is staggering. In some regions, new stars are born at rates thousands of times higher than in our quiet neighborhood. The Scutum star cloud is a dense patch of stars visible from Earth in the constellation Scutum. It contains some of the most luminous stars known, including red supergiants so large they could swallow the orbit of Mars. These behemoths live fast and die in spectacular supernovae. The density here is so high that gravitational interactions are violent. Stars can be ejected from their clusters at high speeds, becoming runaway stars. Some of these refugees travel so fast they will eventually escape the Milky Way entirely, becoming lonely wanderers in intergalactic space. Now we approach the hidden backbone of the galaxy. For a long time, we thought the Milky Way was a simple spiral. We were wrong. At its center, there is a massive elongated bar made of stars and gas. This bar is 27,000 light-years long. It rotates as a solid unit, spinning faster than the spiral arms. It acts like a cosmic pump. This bar is why the galaxy looks the way it does. It funnels gas from the outer regions toward the center. It creates the structure of the spiral arms. Think of it as a funnel. When gas clouds drifting in the outer disk encounter the bar's gravitational field, they get kicked off their circular orbits and spiral inward. This bar instability is what triggers the massive star formation we see in the inner galaxy. Without the bar, the Milky Way would be a much quieter place. The bar is the traffic director, forcing matter down towards the galactic center. We are following that traffic. As we get closer to the center, the normal rules of space begin to break down. We enter the central molecular zone. This is a ring of molecular clouds surrounding the galactic nucleus. It is a region only 1,000 light-years across, but it contains as much gas and dust as the rest of the inner galaxy combined. The density is extreme, but something strange happens here. The star formation rate is actually 10 to 100 times lower than it should be. The gas is there, but it is not collapsing. Why? Because of the extreme conditions near the center. The magnetic fields are thousands of times stronger than in our neighborhood. They are heated by the supermassive black hole and the intense radiation from massive stars. These magnetic fields act like steel cables, supporting the clouds against gravity. They prevent the gas from collapsing into stars. When star formation does happen here, it produces monsters. Stars over 100 times the mass of our sun. They burn blue-white and explode in just a few million years. The gas here is a mixture of extremes. The dense cloud cores are just a few degrees above absolute zero, freezing cold. But the spaces between the clouds are filled with gas heated to millions of degrees by shock waves. It is a bizarre environment where frozen gas exists right next to million-degree plasma. And then we see it, the source. Deep in the heart of our galaxy, something is broadcasting. Radio telescopes on Earth detect a constant stream of signals coming from the galactic center. These signals have traveled 26,000 light-years to reach us. They tell a story of chaos. The radio emissions flicker and flare, sometimes increasing in brightness by factors of hundreds in just minutes. These are the death cries of matter. As gas and dust fall toward the central black hole, they accelerate, heat up, and emit radio waves before crossing the point of no return. The radio signals trace the spiral path of infalling material. They reveal the presence of relativistic jets, narrow beams of matter and energy traveling at nearly the speed of light, blasted outward from the black hole's environment. One of the most dramatic discoveries was the observation of a gas cloud called G2. Astronomers watched in real time as this cloud, with 3 times the mass of Earth, was stretched and torn apart as it approached the black hole. Its radio emissions tracked its destruction over several years. It was a front-row seat to gravitational violence. We have reached the end of our journey. We are at the absolute center of the Milky Way. We are inside the nuclear star cluster. Here, packed into a space smaller than the distance from the Sun to its nearest neighbor, live 25 million stars. The density is unimaginable. Stars are only a few billion miles apart. Their outer atmospheres can brush against each other. Planetary systems would be torn apart in this chaos. Many of these stars are exotic. Wolf-Rayet stars blast away their outer layers in winds traveling thousands of miles per second. Blue hypergiants shine with the light of millions of suns, and at the very heart of this cluster sits the anchor. Sagittarius A star, a supermassive black hole containing the mass of 4 million suns. It is crushed into a space smaller than Mercury's orbit. For decades, we could not see it. Dust blocks visible light. But in the 1990s, astronomers using infrared telescopes tracked individual stars orbiting this invisible point. One star, called S2, orbits the black hole every 16 years. At its closest approach, it races past at 25 million miles per hour. The gravitational forces are so extreme that they cause measurable effects predicted by Einstein's theory of relativity, like the bending of light and the shifting of time. In 2019, the Event Horizon Telescope captured the first direct image of this black hole's shadow. We saw a dark silhouette against a glowing ring of superheated gas. It confirmed decades of theory. This is the end of the line. If we cross the event horizon, the point of no return, we enter a region where our physics breaks down. Tidal forces would spaghettify any object. Time would dilate infinitely from an outside perspective. At the center lies a singularity, a point of infinite density where the laws of physics as we know them cease to exist. But even this monster is not the end. We have to zoom out again, because our galaxy is not alone. Orbiting the Milky Way like moons around a planet are over 50 satellite galaxies. The most famous are the large and small Magellanic Clouds, visible from the southern hemisphere. They contain billions of stars, but gravity is not a gentle force. The Milky Way is pulling on these satellites, stealing their gas and stars. The Sagittarius dwarf galaxy is currently being torn apart, leaving a stream of stars across our sky. This is cannibalism on a cosmic scale. One of the most incredible structures in our sky is the Magellanic Stream. This is a river of hydrogen gas, 600,000 light-years long, trailing behind the Magellanic Clouds. It is the litter of a cosmic meal. The gas has been stripped from the clouds by the Milky Way's gravity over billions of years. This gas is pure, pristine, and it is feeding our galaxy. It will eventually fall into the Milky Way and trigger new generations of star formation. We are living in a recycling universe, and the future is written in the stars. In about 4.5 billion years, our night sky will transform. The Andromeda Galaxy, the largest galaxy in our local group, is racing toward us at 250,000 miles per hour. It is heading straight for us. When galaxies collide, stars rarely hit each other. The space between them is too vast, but the gravitational fields will tear the structures apart. The Milky Way and Andromeda will merge into a giant elliptical galaxy. Astronomers have already named it Milkomeda. Gas clouds from both galaxies will collide, triggering a massive burst of star formation. The supermassive black holes at the centers will spiral together and merge, releasing a blast of gravitational waves that will ripple across the universe. Our solar system will likely survive, but our orbit will be thrown into chaos. we might be flung into the outer suburbs of the new galaxy, or we might be pulled close to the new galactic center. By that time, the sun will be a red giant, so our habitable days will be long gone. But even this massive collision is just a chapter. We have to look even further ahead to the heat death of our galaxy. Over the next 10 billion years, the Milky Way will stop forming new stars. The supply of gas will run out. The massive blue stars will explode. The medium stars, like our sun, will become white dwarfs. Only the tiny red dwarf stars will remain, burning for trillions of years. Eventually, even those will fade. The galaxy will become a dark collection of cold stellar corpses, black holes, and neutron stars, drifting through an ever-expanding universe. The supermassive black hole will swallow whatever stray material is left. On unimaginable timescales, even those black holes will evaporate through Hawking radiation, leaving behind nothing but a faint mist of particles. The Milky Way will be gone. But do not despair. This is the story of all things. The universe is a cycle of creation and destruction. The journey we just took, from our quiet blue planet to the monster at the center and beyond, shows us that we are part of something magnificent. Every atom in your body was forged in a star that died long ago, scattered into space to become part of a new generation. We are not just living in the galaxy. We are the galaxy. We are the universe's way of looking at itself. We are the organized, complex patterns of matter that have evolved to understand the journey. The next time you look up at the Milky Way, remember the speed, remember the violence, remember the beauty, and remember that you are not just observing the universe from a safe distance. You are riding on a wave of star stuff, racing through a cosmic city on a journey around the infinite. But this cosmic city is not a static map. It is a living, breathing ecosystem, and we are still discovering its true architecture. As we zoom out further, we see that our galaxy is embedded in a lattice of galaxies and dark matter that stretches across the observable universe. That lattice is called the cosmic web. The Milky Way, Andromeda, and their satellites form a small knot in that web, but we are just one thread in a tapestry that spans 93 billion light-years. The journey we have taken from the quiet bubble of the local bubble to the violent heart of Sagittarius A is a journey not only through space but through time. Every step we took revealed another layer of complexity. The sun's orbit is not a simple circle. It bobs up and down through the galactic plane every 33 million years, and each crossing exposes Earth to higher doses of cosmic radiation. Some scientists believe these crossings may have triggered mass extinctions, like the one that wiped out the dinosaurs 66 million years ago. We are not just passengers on a merry-go-round. We are riding a roller coaster that dips into dangerous neighborhoods. Recent data from the Gaia spacecraft has given us the most precise map of the Milky Way ever created. It has tracked the motions of nearly 2 billion stars. What we have learned is humbling. The galaxy is not a perfect disk. It is warped. The outer edges are bent upward on one side and downward on the other, like the brim of a fedora hat. This warp is likely caused by a collision with another galaxy hundreds of millions of years ago, or perhaps by the gravitational pull of the Magellanic Clouds as they orbit us. We have also discovered that the Milky Way is not a closed system. It is constantly accreting new gas from intergalactic space, feeding the star formation that keeps our galaxy alive. High-velocity clouds of hydrogen, are falling into the galaxy at speeds of hundreds of kilometers per second. They are the ghosts of ancient cosmic floods, bringing fresh fuel from the void. Without this influx, the Milky Way would have run out of star-forming gas long ago. And then there are the ghostly structures that we cannot see but can detect through gravitational lensing. The dark matter halo that surrounds our galaxy is not a smooth sphere. It contains clumps and streams, the remnants of smaller galaxies that were torn apart and absorbed billions of years ago. One such stream, the Sagittarius stream, wraps around the entire galaxy like a scarf. It is the fossil of the Sagittarius dwarf galaxy, which is still being cannibalized today. Our galaxy is a predator, and it has been eating its neighbors for eons. But perhaps the most profound discovery is that the Milky Way is not ordinary. It is a barred spiral galaxy with a quiet supermassive black hole. Many galaxies in the universe have much more active black holes, blasting out jets that disrupt entire star systems. The fact that our black hole is relatively quiet may be one reason life was able to evolve on Earth. We are living in a cosmic safe zone, shielded not only by the local bubble, but also by the black hole's inactivity. Now, look outward again. Beyond our local group lies the Virgo cluster, a massive collection of over 2,000 galaxies. Our local group is falling toward that cluster at over 1 million miles per hour. But the Virgo cluster itself is moving. It is being pulled by the Great Attractor, a gravitational anomaly that lies behind the plane of the Milky Way, hidden from our view. The Great Attractor is actually the center of the Laniakea supercluster, a structure so vast that it contains 100,000 galaxies and spans 500 million light-years. We are inside one of its spiral arms, just as our solar system is inside the Orion arm of the Milky Way. The layers of nested structures are endless, and beyond Laniakea, there are other superclusters, and beyond them, the cosmic web. At the largest scales, the universe looks like a network of filaments separated by giant voids, empty regions hundreds of millions of light-years across. The Milky Way sits on the edge of one such void, the local void, which stretches for over 100 million light-years. We are on the boundary between the dense cosmic cities and the cosmic deserts. This journey reveals something essential. We are not the center of the universe. We are not even the center of our own galaxy. But we are special. We are the only known species that can map its own home, that can understand the forces that shape it, and that can wonder about its fate. The end of the Milky Way is not a tragedy. It is a transformation. The atoms that once made up our sun, our planet, and our bodies will be recycled into new stars, new planets, and possibly new life. The carbon in your DNA will one day be part of a star in a distant galaxy. The iron in your blood will be forged in a supernova that has not yet exploded. We are not just passengers on this journey. We are the journey itself. So the next time you look up at the Milky Way, do not just see a band of light. See the history of the universe. See the violence of birth and death. See the slow, majestic dance of gravity and time. See the cities of stars, the rivers of gas, the black hole at the center, the dark matter that holds it all together. And remember that you are not separate from this cosmic story. You are a part of it, a temporary, conscious pattern of matter that has arisen from the dust of dead stars to witness and understand. The journey around the Milky Way is infinite, but our time here is finite. Make it count. And as we sit here At the end of this journey, it is worth asking the most human question: are we alone in this vast galactic city? The journey we have taken, from the quiet suburbs of the local bubble, through the bustling star-forming regions of the Orion Arm, past the ancient globular clusters, into the violent maelstrom of the galactic center, has shown us a galaxy teeming with the raw ingredients for life: carbon, oxygen, nitrogen, phosphorus, sulfur, iron. Every element necessary for biology, as we know it, is scattered across the Milky Way, forged in stars and spread by supernovae. The building blocks are everywhere, but are they ever assembled? The search for life beyond Earth has focused on our own neighborhood first. Mars, once warm and wet, now a cold desert. Europa, an icy moon of Jupiter, hiding a liquid ocean beneath its crust. Enceladus, spraying organic molecules into space. These are tiny steps, barely a light second from our home. But the galaxy is vast, and the odds seem to favor life. Consider this. In the past decade, the Kepler Space Telescope and its successors have found that most stars in the Milky Way host planets. Roughly 1 in 5 Sun-like stars has an Earth-sized planet in the habitable zone, the region where liquid water can exist. That means, in our galaxy alone, there could be 10 billion potentially habitable worlds. 10 billion! And yet, we have heard nothing. The sky is silent. This is the Fermi paradox, the contradiction between the high probability of extraterrestrial life and the lack of evidence. Where is everybody? Some suggest that intelligent civilizations inevitably destroy themselves through war, resource depletion, or environmental collapse. Others propose that they choose not to communicate, or that they exist in forms we cannot recognize. Perhaps the journey around the Milky Way is so long, and the distances between stars so vast, that no civilization has ever bridged the gap. Our solar system may be an island in a cosmic ocean, drifting alone. But there is another possibility, one that emerges directly from the journey we have just taken. The galactic center is dangerous, filled with radiation, stellar collisions, and the gravitational grip of a supermassive black hole. The outer edges of the galaxy are sparse, with fewer heavy elements to build rocky planets. We are located in the galactic habitable zone, a narrow band where conditions are just right. Not too much radiation, not too little metallicity. This zone may be very thin. Perhaps intelligent life is rare because the conditions for its emergence are rare. The journey we took to the center was a journey toward death. The journey outward is a journey toward scarcity. We are perched in a sweet spot, a cosmic Goldilocks region. And within that region, the timing is everything. The Milky Way has existed for over 13 billion years. The first generation of stars had no planets with heavy elements. The second generation began to produce rocky worlds. Life on Earth emerged about 4 billion years ago. Complex life. We live in a vast, open universe. It is filled with trillions of galaxies, each containing hundreds of billions of stars. Space is so enormously large that we can never hope to know every single galaxy. But with telescopes like Hubble and James Webb, we have mapped the positions of billions and have stared all the way out to the farthest corners of the cosmos. Today, we will use this wealth of understanding as we embark on the ultimate journey, one that will take us through all of space and time. We will venture beyond our galaxy to the farthest horizons, taking stock of the most jaw-dropping and significant landmarks along the way. This is our journey, a journey to the edge of the universe. Before we begin our cosmic journey, it is important to know where we are headed and where the edge of the universe really lies. When people talk about space, most of the time they are referring to the observable universe, also known as the Hubble volume. This is a spherical geocentric slice of space which surrounds the Earth, containing all the galaxies and matter that can be observed by our instruments because their light emissions have had time to reach the solar system. As we know, light travels omnidirectionally into space from a luminous source at a finite speed of just under 300,000 kilometers per second. While this is exceptionally fast on earthly scales, over the largest cosmic distances, it is agonizingly slow. Any meaningful intergalactic distance beyond the Milky Way incurs a substantial light delay in the emissions reaching Earth. This causes objects to appear younger, and it is why astronomers find so much use in using light years as a unit of measurement. If a galaxy lies 1 billion light years from Earth, we see it as it was 1 billion years ago. In this sense, the edge of the universe is a time barrier as much as anything, constrained by its finite age of 13.8 billion years. The Hubble volume only contains galaxies whose light has had to travel less than 13.8 billion light years to reach Earth. The farther the galaxy, the closer to the birth of the universe 13.8 billion years ago it appears to be. Thus, a journey to the edge of the universe is also a journey back to the beginning of the universe. There is an old saying that a telescope is a time machine. A telescope like James Webb is a TARDIS, whose ultra-sharp infrared eyes are, thus, at this very moment, staring deeper into space than ever before, allowing us to know the cosmos at every single stage of its life. Throughout all of this life cycle, the universe has been expanding in volume. We can see evidence of this ingrained upon the light reaching us from space, which arrives elongated and reddened due to a phenomenon known as redshift. Redshift occurs when patterns of photons traveling towards Earth experience a decrease in wavelength, in this case because they are being separated by the expansion of space. As empty space inflates like a balloon, the creation of new space everywhere gently widens the gaps between objects, including traveling waves of light over very vast distances. This has the effect of turning visible light red, but the phenomenon applies to all types of electromagnetic radiation and thus is a useful corroborator of intergalactic distances. The redshift value of a given object, denoted by the letter Z, provides us with the perfect scale with which we can begin our cosmic journey. Our journey begins on Earth, a tiny, indistinguishable speck of space even when compared with the rest of the solar system, let alone the rest of our galaxy. The Sun is just one of at least 100 billion stars, many of which will host planetary systems like our own. But the true terrifying scale of the universe does not really begin to become apparent until we escape the bounds of the Milky Way. Our galaxy is the second largest member in a small and sparse pocket of space known as the local group, which contains more than 30 galaxies and hundreds of smaller satellite galaxies. The local group extends about 10 million light-years, though its four most significant galaxies all lie within a relatively close proximity. In fact, the group's three largest members appear to be on a collision course as they are drawn together by gravity overcoming the weak expansion of the universe. Therefore, we do not notice any sort of redshift until we travel beyond the local group. Outside its bounds, we stray into the wider local volume, another smaller geocentric slice of local space, encompassing all the galaxies within about 30 million light-years of Earth, extending out to around redshift 0.02. This volume contains us and the rest of the local group, alongside more than 500 other fascinating nearby galaxies, each arranged into their own local aggregations. One such not-so-local group is the Council of Giants, a ring of 12 galaxies roughly the size of the Milky Way, or larger, which appear to surround our local group. Being so large and massive, many of these galaxies also host their own smaller extragalactic neighborhoods, like the Sculptor Group, hosted by the Council of Giants Sculptor Galaxy. Officially designated NGC 253, the Sculptor Galaxy lies around 11 million light-years from Earth and is classed as a starburst galaxy, a galaxy undergoing a vigorous period of star formation, making it one of the most intrinsically luminous galaxies within our local slice, surpassed only by our neighbor, the Andromeda Galaxy, and the more distant Sombrero Galaxy. Messier 104, better known by its sombrero-like galactic bulge and dust ring, is a bizarre, unique galaxy of an unclear morphology. Its galactic halo glows with starlight, brighter than the Sculptor Galaxy, despite being only half the size and lying 3 times farther from Earth. It belongs to a series of about 100 small galaxies known as the Virgo II cloud, which trail off from the most substantial Virgo cluster found within its namesake constellation. Lying some way beyond the local volume at redshift 0.039, the Virgo cluster is a packed city center structure of galaxies containing more than 1,500 in what is the most substantial aggregation in our immediate intergalactic vicinity. Close to its heart, we find a truly iconic titan of the cosmos, Messier 87. This supergiant elliptical galaxy is home to several trillion aging evolved stars and more than 15,000 globular clusters spread across an expanse far larger than our Milky Way galaxy. At its core, we find its central supermassive black hole with a mass more than 6 billion times that of our Sun. It was this black hole which dazzled the world in 2019 as the first ever to be imaged by the Event Horizon Telescope's decade-long quest to bring one into view. This black hole is also a keen target for radio astronomers, as it blasts a high-energy stream of plasma for thousands of light-years into space, one of the most prominent extragalactic sources in the radio sky. This galaxy, along with its surrounding Virgo cluster and the branching Virgo II clouds, as well as us and more than 100 additional large galaxy aggregations and groups, all appear to feed into an even greater intergalactic structure which takes us all the way beyond the boundary of redshift 0.01, around 150 million light-years. The Virgo supercluster, as it is known, is home to thousands of galaxies spread across an expanse exceeding 100 million light-years. And the scale of aggregations within the cosmic web does not even appear to end there either. The Virgo supercluster is just one of 4 lobes within an even larger apparent network of galaxies defined by the velocities and motions of their flows across space. This higher-order galaxy supercluster is known as Laniakea. It contains more than 100,000 galaxies as it stretches for more than 500 million light-years across space. While these galaxies are not gravitationally bound and thus are not capable of overcoming the universe's expansion to congregate, the combined gravitational potential from within this network does induce some superficial movement on its constituent galaxies, analogous to the way in which photosynthetic leaves stretch towards the sunlight. But for a long time, we did not know what these galaxies were stretching towards, as the apparent gravitational basin of Laniakea is situated in a region of the sky that is obscured by the Milky Way's galactic plane. Therefore, the source of this so-called great attractor of galaxies remained a mystery for many decades. Thankfully, new surveying capabilities have since helped to illuminate this zone of avoidance hidden behind the Milky Way. Unlike visible light, X-rays and infrared emissions can pass through the thick, dusty disk of our galaxy, allowing us to detect the superclusters lying beyond. We find the source of the great attractor located deep within the Centaurus supercluster. Inside this supercluster, 250 million light-years from Earth at redshift 0.018, we find the Norma cluster, the apparent heart of the great attractor, towards which Laniakea's bulk flows seem to be angled. But this galaxy cluster alone is not substantial enough to account for the speed at which galaxies seem to be attracted towards this basin. Something significantly larger is also exerting an influence. Lying well beyond the bounds of Laniakea, more than 650 million light-years from Earth, we find the Shapley supercluster, an exceptionally packed massive supercluster concentration containing thousands of gravitationally bound condensing galaxies. Slightly farther beyond that, more than 870 million light-years from Earth, we find the Pisces Cetus supercluster. It is now believed that these two more substantial galaxy superclusters are each exerting gentle influences on the galaxies of Laniakea from afar, amplifying the potential of the Norma cluster, which explains what makes the gravity of the great attractor so great. As we mentioned, the Laniakea supercluster is not gravitationally bound, unlike the Shapley concentration, and neither are the other galaxies of the Virgo supercluster. So, it is hard to say whether we can really call these types of higher-order aggregations structures. However, propagations in the cosmic web can reach even larger scales than a supercluster, known as a galaxy filament. Galaxy filaments are the largest type of cosmic structure, manifesting as chains of galaxy superclusters, assuming thread-like formations over distances exceeding 250 million light-years. And some can get even larger still. 1 billion light-years from Earth at redshift 0.074, we find the Sloan Great Wall, a truly colossal filament-like structure, identified from data recorded by the Sloan Digital Sky Survey. This structure constitutes a giant arcing formation of galaxies within a fairly dense region of space. It contains several packed galaxy superclusters, the largest of which, S126, can be found near its center. The full structure measures more than 1.3 billion light-years by its largest extension, although it has been argued in the years since that this enormous scale may actually be the result of 3 aligning galaxy superclusters and filaments as opposed to one long, unbroken chain. But the Sloan Great Wall was nonetheless instantly crowned as the largest known cosmic structure upon its discovery, a title it would hold for around a decade. As we pass through the Sloan Great Wall, we reach the boundary of redshift 0.1, around 1.38 billion light-years from Earth. Beyond this point, our light delay approaches and exceeds 1.5 billion years. So from this distance, we start to see objects more characteristic of the younger universe billions of years ago. Galaxies like the Milky Way and M31 were still undergoing major evolutionary changes as they collided with neighboring galaxies, combining their stars and gas. These mergers flooded the cores of galaxies with abundances of star-forming gas, which was invigorated by contrasting tidal influences associated with the merger. When a large amount of gas collects at the center of a galaxy, particularly around its black hole nucleus, all sorts of weird and wonderful electromagnetic processes can arise. When a galaxy's central black hole interacts with this gas, we call it an active galactic nucleus, because it invariably leads to the release of an enormous amount of radiant energy, amplifying the galaxy's luminosity in at least some electromagnetic wavelengths. For example, in the radio spectrum, radio galaxies are one such type of active galactic nucleus, invariably occurring within elliptical galaxies like M87. As gas orbiting this galaxy's nucleus is ionized, subatomic particles become entrapped within the black hole's magnetic field and are funneled onto its polar axis. This matter is then blasted away from the event horizon at near light-speed velocities by a pair of twin relativistic jets, carrying the material off at high energies for thousands of light-years into space. This stream of ejecta glows with radio-loud synchrotron radiation, and sometimes these emissions can reach far larger scales than the optical emissions of the underlying host. Thus, radio galaxies are much more detectable at higher redshifts than the increasingly faint optical emissions of radio-quiet galaxies. Beyond redshift 0.1, we find 3C 327, one of thousands of known radio galaxies. Around 1.5 billion light-years farther, we find the current largest known radio galaxy, Alcyoneus, its emissions extending a whopping 16 million light-years in length. But between these two objects, at redshift 0.158, we find 3C 273. But this is not just a radio galaxy. It is a quasar, the brightest and most energetic type of active galactic nucleus. Unlike within a radio galaxy, which is driven by the jets emanating from the nucleus, a quasar's emissions are driven more so by the accretion disks surrounding the black hole. Within a spinning accretion disk, subatomic particles race round at extraordinary velocities, smashing into other particles and releasing thermal energy through friction. This friction superheats the material in the disk to millions of kelvins, and often even hotter, causing it to radiate electromagnetic energy and light some 50 times more efficiently than the nuclear fusion reaction enabling the shining of the sun. This results in the release of unfathomable quantities of luminous radiant energy almost uniformly across the electromagnetic spectrum. Quasar galaxies shine hundreds of thousands of times brighter than the Milky Way, so powerful that they can impersonate the stars in our galaxy from billions of light-years beyond Earth. In fact, they were only discovered due to their prominence in other wavelengths, specifically 3C 273's unusual radio and ultraviolet emissions profile for what was once thought to be an ordinary star. But quasar galaxies tend to be seen rather infrequently within this redshift band. 3C 273 lies around 2.5 billion light-years away, but the vast majority lies significantly farther back, in a time when space was generally better suited for the ignition of these ultra-bright intergalactic beacons. In addition to requiring abundances of gas in orbit around a galactic nucleus, a black hole itself needs to be a particular size in order to drive a quasar's emissions. If a supermassive black hole is too massive, like the monster at the heart of M87, then it will be too large to shred gas within its ergosphere, tending to gulp material rather than chewing it up. And it is this chewing motion, the tidal gradient exerted on objects by smaller black holes, that spaghettifies gas and separates it into subatomic particles which feed its accretion disk. Thus, back in the early universe, when black hole nuclei at the hearts of galaxies were generally smaller, we see far more of these intergalactic wells of light dotted around space. But to see quasars in their highest abundance, we need to venture much further into space, across the boundary of redshift 1, just under 8.4 billion light-years from Earth, back when the universe was considerably younger and smaller, less than half its current age. At this depth, quasars begin to pop into view at substantially higher rates, which is convenient given that most of the light from ordinary galaxies at these distances is too dim and faint for us to study in any detail. But quasars shining all the way from the peak quasar epoch, just under 10 billion years ago, are capable of elucidating the galaxy filaments upon which they once shone like LED lights around the branches of a Christmas tree. Approaching 9 billion light-years from Earth, we start to see quasar galaxies in numbers and formations that emulate vast cosmic structures like the Sloan Great Wall. Large quasar groups are assortments of quasars scattered over multi-billion light-year distances, and though the groupings themselves are not believed to be gravitationally linked, their aggregations still rank among the largest structures we have ever seen. Gazing 8.8 billion light-years from Earth, we find the first of 3 record-breaking quasar groups, U1.11. It contains 38 quasar galaxies spread over a distance of 2.2 billion light-years by largest extension. Lying adjacently but somewhat further behind at redshift 1.28, we find the Claus-Campusano LQG, another cluster of 34 quasar galaxies also appearing to span a distance in excess of 2 billion light-years. Finally, around that same distance at redshift 1.25, we find the largest grouping of them all, the huge LQG, an assortment of 73 quasar galaxies spread across an expanse greater than 4 billion light-years. In truth, none of these assortments are likely to be indicative of real structures. They are more likely to be the product of random alignments within which we can see patterns. But in any case, scientists do still rank these 3 quasar groups among the list of largest known cosmic structures. But the very largest structure, which displaced the Sloan Great Wall in 2013, is not a quasar group. It is a gamma-ray burst formation. A gamma-ray burst is the most powerful type of electromagnetic explosion, releasing as much energy as the Sun's entire life cycle in a matter of seconds. Unlike quasars and radio galaxies, gamma-ray bursts do not tend to be associated with active galactic nuclei. Rather, they often occur as a result of exceptionally violent supernova explosions or when a pair of neutron stars collide to form a black hole. In both cases, a catastrophic quantity of gamma radiation is released, lasting anywhere from a few milliseconds to a number of hours, followed by a more persistent afterglow in longer wavelengths, which allows us to map the positions of hundreds. Lurking well beyond the quasar groups at redshift 1.6, scientists found an apparent aggregation of gamma-ray bursts scattered over an extraordinary expanse of 10 billion light-years, termed the Hercules Corona Borealis Great Wall. While scientists do take this wall to be the largest cosmic structure, its concentration is not likely to be the result of an underlying superfilament. After all, gamma-ray bursts like quasars are an intrinsic event to a galaxy and therefore likely have little relevance to the evolution of filaments in a wider context. However, simply attempting to comprehend a distance of 10 billion light-years is a mind-melting task. It is inconceivable. It dwarfs our entire existence by orders of magnitude and makes our toils here on Earth feel like nothing. The Hercules Corona Borealis Great Wall takes us all the way out to Redshift 2, 11.2 billion light-years from Earth. Now we arrive back in the early universe, in the midst of one of the busiest times of its life, cosmic high noon, the period when star formation rates in the young universe rose to their highest level. Around 2.5 billion years after the Big Bang, we see the universe dotted by a flurry of gaseous young galaxies, star factories, each of them grinding out the equivalent of 3,000 to 4,000 suns worth of new stars per year, compared to the measly 10 suns worth churned out by the much larger Milky Way galaxy. These early galaxies would have been hives of pervasive ionizing electromagnetic radiation, and luminous quasar galaxies continue to feature prominently throughout this redshift band. But at these insane depths, we sometimes see the emissions from bright active galactic nuclei obscured by foreground walls of gas. Anybody fancy a hot dog? Well, in this case, a hot dog is a hot dust-obscured galaxy, a luminous quasar galaxy from the early universe shining from within a thick covering of surrounding gas. In 2010, NASA's WISE telescope identified more than 1,000 of these hot dogs between redshifts 2 and 4. Now, we are approaching 13 billion light-years look-back time from Earth. However, at redshift 3, the light from objects becomes increasingly difficult to work with, because around this distance, some models of redshift hold that the recessional velocity of galaxies starts to exceed the speed of light. As we mentioned, the inflation of all parts of space pushes galaxies away from each other by widening the gaps in between. So, eventually there comes a distance between 2 points where space will appear to be expanding faster than light speed. But this does not break any laws of physics, because nothing is actually moving at light speed. More than 12 billion light-years from Earth, objects are being pushed away so fast that their emissions become impossibly faint and redshifted, appearing to freeze in time as their light cones are starved of photons and throttled by the universe's expansion. In fact, the redshift bands beyond this distance were once thought to be largely inaccessible, but humanity's next generation of electromagnetic observatories, particularly aided by advancements in the field of infrared, are helping to bring the vanishing lights from this bygone age out of the shadows. Primordial galaxies are one of the principal targets of the James Webb Telescope. Among the breadth of reasons that make these galaxies attractive to astronomers is their hypothesized concentrations of population 3 stars, the universe's first generation of stars which emerged directly from gas left behind by the Big Bang. When these first stars began to shine at the cosmic dawn, it triggered a period in the universe's life which we have so far struggled to gain clear insights on: the epoch of ionization, one of 2 major phase transitions for the early universe's gas. After the Big Bang ended, its plasma was harvested to form the first neutral hydrogen and helium gas. But as this gas gave rise to population 3 stars, their irradiating stellar emissions began to reverse this process, re-ionizing the gas as its electrons were stripped by ultraviolet radiation. Lasting about 150 million years and concluding at redshift 6, the epoch of reionization ended when the majority of the once neutral gas had been converted back into charged plasma. A key question for astronomers studying this age is, Was the universe's reionization shared democratically among all galaxies? Or was the majority driven by a few large galactic oligarchs, which acted as ionization powerhouses? To answer this question, astronomers have attempted to find the farthest, oldest galaxies following the cosmic dawn. In recent years, we have managed to spot objects at astounding depths of more than 13 billion light-years. Within the constellation of Ursa Major, lying at a depth of redshift 11.1, we find GN-Z11, one of the oldest and farthest galaxies we know of, a tiny torrid pocket of gas and ancient stars. This faint smudge is thought to have taken shape only 420 million years after the Big Bang, a remarkably fast buildup when you consider that stars probably did not even exist for more than half of that time. GN-Z11 held the title of the farthest detected galaxy only until as recently as 2022, when astronomers at the University of Tokyo managed to bring an even more remote, and thus earlier, galaxy into view. This galaxy, termed HD1, is estimated to lie at a staggering redshift of 13.27, meaning it formed a mere 330 million years after the birth of the universe, well within 100 million years of the first stars. However, this insane distance is awaiting confirmation from the James Webb Telescope, which, as it happens, also spied its own ultra-distant primordial galaxy recently, GLASS Z13. While not quite as distant as HD1, this Genesis galaxy still lies in the redshift 13 band, 13.5 billion light-years from Earth. It is difficult to comprehend such a vast universal distance, but it becomes even wilder when we factor in the expansion of space. 13.5 billion light-years is how far away these three galaxies were when their first light was emitted. The present-day versions of these galaxies will lie much further beyond, having been cast away faster than the speed of light by the cosmic tide. The proper distance of these galaxies today is now estimated to be more than 33 billion light-years from Earth, so unfathomably remote that their light emissions would never possibly have enough time to reach the solar system now. As objects begin to fall off the grid like this, we approach the edge of the universe. At redshift 20, 13.6 billion light-years from Earth, our optical view of the universe ends with the light from the very first population 3 stars. Beyond this, we stray into one of the most mysterious times in the infant universe's life, its dark age, the time that came after the Big Bang, but before the cosmic dawn, when there were no light-emitting sources and space was completely dark. We know this because space itself is not black. It is colorless and transparent. The blackness that we see undercutting the deep fields snapped by Hubble and Webb is actually a point in the universe's life only a few million years after the Big Bang, where there was no light. Unfortunately, this is as far as it is possible for us to look in the optical wavelengths, at least. Beyond this boundary, no other photons have had time to reach Earth, as they would have been farther than 13.8 billion light-years when they were emitted. As the universe ages, more ancient lights will arrive in the solar system from even greater depths, growing our observable universe. But these galaxies will merely manifest as dark, elongated red shadows frozen in time. Until then, we are confined to the Hubble volume, segmented from the rest of the universe by the cosmic event horizon, also known as the particle horizon. But it is not quite here that the edge of our universe lies. We do have one final stop on this journey. From our point of view, the Dark Age starts where reionization leaves off at redshift 20, but it extends all the way back to redshift 1090, where we find the oldest light in the universe, the afterglow of the Big Bang. This afterglow has been so greatly elongated by the universe's expansion that these are not photons of optical light anymore. They have been shifted into the radio spectrum. No matter where one points an antenna in the sky, there is always a consistent microwave band static that sounds the same everywhere. While most of this owes to Earth-based interference, a small portion originates from a much more profound source, the birth of the universe. The final stop on our cosmic journey is the universe's very own baby picture, a snapshot of the moment the Big Bang ended, when it was just 379,000 years old. This cosmic background radiation began its journey as optical light emitted by the vanishing high-energy plasma, which condensed to form the first atoms. All the photons that came before this moment were absorbed by the primordial plasma before it disappeared and are thus undetectable to us today. So, for all intents and purposes, the cosmic microwave background is as much the edge of the universe as a twilight curtain. The radius of our observable universe is measured by the distance traveled by its oldest lights. These CMB photons have been streaming around freely for 13.8 billion years, but the space they have traveled through now has an expanded proper distance of some 46.5 billion light-years. This is why you might have heard people say that the observable universe is 93 billion light-years in diameter, despite being less than 14 billion years in age. However, this diameter is arbitrary to our observable field, defined by our position in space, the universe's age, and the travel time of light. Were we to travel billions of years across space, our observable universe and particle horizon would shift accordingly. And then, looking back, the Milky Way would become a young red-shifted galaxy. Alas, the edge of our observable universe is not the actual edge of the universe. Most scientists agree that far more lies hidden beyond the cosmic horizon. But the questions of what, how much, and where the real edge lies are different matters entirely. And in the next video, we will aim to answer these questions as we cross over the particle horizon and venture into the darkness of the unobservable universe. But for now, let us pause and reflect on the sheer enormity of the journey we have just taken. Imagine, if you will, that we shrink the entire observable universe down to the size of a familiar object, say, a standard globe of the Earth. On this scale, our Milky Way galaxy would be smaller than a single grain of sand. The entire local group, including Andromeda and dozens of other galaxies, would fit within a tiny cluster of sand grains no larger than a pinhead. The Virgo supercluster, with its thousands of galaxies, would be about the size of a small coin. Laniakea, that enormous collection of 100,000 galaxies, would stretch across a region roughly the size of a dinner plate. The Sloan Great Wall, the quasar groups, the Hercules Corona Borealis Great Wall, all of these would be faint lines and smudges across this globe, barely visible to the naked eye. And yet, this entire globe represents only what we can see. Beyond its surface, there is an even larger sphere of potential cosmos, an unobservable universe whose true size we can only guess at. Now, consider the analogies we use for distance. When we say a galaxy is 10 billion light-years away, what does that mean in human terms? Light travels at 300,000 kilometers per second. In 1 year, light covers about 9.5 trillion kilometers. To travel 10 billion light-years, you would need to multiply that by 10 billion. That number is so large that it has no practical meaning. So instead, let us think in terms of time. The light from that galaxy began its journey when the Earth did not yet exist, when the sun was just a glimmer in a nebular cloud. That light has been traveling for twice the age of our planet. It is the oldest message we have ever received, and as we zoom further back, the time deepens. At a redshift of 11, we see a galaxy that existed when the universe was only 4% of its current age. The stars in that galaxy were among the first to ignite, and they have long since died. The light we see today is a ghost, a fossil of a time when the cosmos was still in its infancy. By the time we reach the cosmic microwave background, we are looking at the universe when it was just 379,000 years old, a mere blink in cosmic history. That radiation is the fingerprint of the Big Bang itself, a whisper from the dawn of time. Yet, for all our telescopes and calculations, there is a humbling truth. We are trapped inside our own light cone. The particle horizon marks the limit beyond which we will never see, no matter how long we wait. Because the universe is expanding, some regions are moving away from us faster than light, and their photons will never reach us. That means there is a vast, unknowable realm out there, maybe infinite, maybe finite, but forever hidden. Some models suggest that the unobservable universe is at least 250 times larger than what we can see. Others propose a truly infinite cosmos, with countless Hubble volumes beyond our own, each containing its own set of galaxies, stars, and possibly even copies of ourselves. But we must be careful not to let our imaginations run wild without evidence. The scientific consensus is that the observable universe is all we can ever study directly. The edge we see is not a wall, it is a horizon. And just as the horizon on Earth appears as a line where the sky meets the ground, yet we know that the ground continues beyond. So too does the universe continue beyond our cosmic horizon. The difference is that we can walk to the earthly horizon. We can never reach the cosmic one because the universe is expanding and the horizon recedes as we move. It is a horizon that will always remain just out of reach. So, what lies beyond? That is a question that has fascinated humanity for centuries. In the next part of this series, we will explore the theories, the multiverse, bubble universes, eternal inflation, and the possibility that our observable universe is just one tiny patch in an unimaginably larger tapestry. We will also confront the ultimate fate of the cosmos and what the edge of the universe means for the future of intelligent life. But for now, let us take a moment to appreciate the journey we have already taken. We started on a small, fragile planet orbiting an ordinary star in the suburbs of a spiral galaxy. We have soared through the local group, past the Virgo cluster, through Laniakea, and out into the vast cosmic web. We have witnessed the birth of stars, the fury of quasars, and the silent glow of the first light. We have traveled 13.8 billion years back in time, and we have reached the very limits of our vision, and yet the universe stretches far beyond, an endless ocean of possibility. The edge is not a place, it is a boundary of knowledge, and it is our insatiable curiosity that pushes us to peer ever further, to ask what lies beyond the horizon, and to dream of the day when we might finally understand the whole of creation. Thank you for joining me on this ultimate journey to the edge of the universe. If you enjoyed this voyage, please like and subscribe, and stay tuned for the next episode, where we will cross the cosmic horizon and explore the mysteries of the unobservable universe. Until then, keep looking up. Imagine standing on the surface of a world so isolated that the night sky above you holds nothing but a faint milky smudge of stars, your own galaxy. And beyond that, an endless, absolute blackness. No pinpricks of distant suns, no blur of neighboring galaxies, just the slow, silent drift of darkness in every direction. You would not know, for the first few decades of your civilization's existence, that anything else exists at all. Your telescopes would reveal only the stars of your own home, and then, eventually, a few dim, unresolved clouds that might be entire galaxies, but so far away, so impossibly remote, that they appear as nothing more than ghostly whispers on the edge of detection. This is not a scene from a science fiction novel. This is what reality would feel like if humanity had evolved inside one of the universe's great cosmic voids. We live in a universe that is, by and large, staggeringly empty. If you stand atop the Shard in London on a clear day, you can look south and see the coast of France. The air between seems empty, transparent, but it contains roughly 10 trillion atoms per cubic meter. That is an enormous number, yet we call it empty. Go up 100 kilometers, and the density drops to 1,000,000 trillion atoms per cubic meter. A third of the way to the moon, you find about 7 million atoms. Leave the solar system entirely, and interstellar space, the space between stars, contains approximately 1,000 atoms per cubic meter. Travel even farther, into the space between galaxies, and you are down to just 10 atoms per cubic meter. That is emptier than the best vacuum ever created on Earth by a factor of trillions. And yet, that is not truly empty. The space between galaxies is still part of something larger, the cosmic web, a vast network of filaments and walls where galaxies gather in clusters and superclusters. But what about the spaces in between those filaments, the gaps between the largest structures of the universe? Those regions are emptier still, and they have a name: voids. A void is a vast, roughly spherical region of space with a dramatically lower density of galaxies compared to its surroundings. The technical definition used by astronomers refers to an area where the number of galaxies is about 1/10 the typical number found in the galactic walls and filaments that define the cosmic web. Voids are not structures themselves. They are the empty spaces between structures, but they are a fundamental part of the universe's architecture. The smallest voids are about 10 megaparsecs across. 1 megaparsec is roughly 3.26 million light-years, so a typical small void is about 30 million light-years in diameter. Larger typical voids can reach 10 times that size, 300 million light-years across, and at that scale, we call them supervoids. But even that is modest. Some voids, especially those that form in the low-density regions of the universe, far from the densest walls, can stretch over 1 billion light-years in diameter. To appreciate that scale, 1 billion light-years is so vast that light, traveling at 300,000 kilometers per second, takes 1 billion years to cross it. That is 1/10 the age of the universe itself. The study of cosmic voids began in earnest in the 1970s, when redshift surveys first allowed astronomers to map the three-dimensional distribution of galaxies. Before then, we saw the universe as a more or less uniform scatter of galaxies. But as we measured their distances by the redshift of their light, a structure emerged. Galaxies were not randomly distributed. They clustered into filaments, walls, and nodes, with enormous empty regions in between. The first void to be recognized was identified in the direction of the Coma cluster in the late 1970s. By 1981, a particularly striking example was discovered, the Bootes Void, lying near the constellation of Bootes on the edge of the Hercules supercluster. This void was enormous. Estimates ranged from 250 to 330 million light-years in diameter, with a volume of over 200,000 cubic megaparsecs. At the time, its size was so unexpected that some scientists questioned whether there had been enough time in the universe's history for such a void to form. But further observations revealed that the Bootes Void is not a single empty bubble. It is the result of two smaller voids merging, like soap bubbles coalescing into one larger cavity. The galaxies that should have filled that space were swept to the edges, leaving behind a nearly empty interior. And yet, it is not completely empty. Astronomers have found about 60 isolated galaxies inside the Bootes Void, where thousands would be expected in a comparable volume of normal space. Those 60 galaxies form a tube-like structure running through the void's center, the remnants of the boundary between the original merging voids. To put that emptiness into perspective, imagine driving from the Atlantic coast of the United States to the Pacific coast and passing only a couple of small towns along the way. And that analogy fails because the void is three-dimensional. The Bootes Void is so sparse that it has earned the nickname the Great Nothing. If humanity had evolved on a planet inside one of those 60 isolated galaxies, we would not have known that other galaxies existed until the 1960s. That is not hyperbole. Astronomer Greg Aldering of the University of Minnesota calculated that the nearest external galaxy would have been so far away that it would have taken decades of technological advancement just to detect it. Imagine the scientific revolution delayed by half a century because the universe simply appeared empty. Now, let us consider the nature of these voids. How do they form? The answer lies in the first tiny fraction of a second after the Big Bang. During that initial moment, the universe was an infinitesimally small, ultra-dense soup of energy. Quantum fluctuations, random variations in energy density, created ripples across this primordial plasma. Then, an event called cosmic inflation blew the universe up from microscopic to astronomical in a fraction of a second. Those quantum ripples were stretched across vast distances. The denser spots became the seeds of future galaxies and clusters. The emptier spots became the seeds of voids. As the universe expanded and cooled, dark matter began to clump together under gravity, forming a network of filaments. Normal matter followed, condensing into gas clouds, then stars, then galaxies. Over billions of years, the galaxies migrated along these filaments, gathering into clusters and superclusters. Meanwhile, the regions that had been slightly less dense from the beginning were drained of matter. Gravity pulled everything out of those regions, leaving behind vast, nearly empty spaces. These are the voids we see today. Voids are not just empty, they are dynamic. They grow as the universe expands, because the dark energy that accelerates cosmic expansion acts everywhere, including inside the voids. The empty space inside a void expands faster than the denser regions because there is less matter to slow it down. This means that voids become larger and emptier over time. Their size and shape can tell us about the abundance of dark energy. In fact, by studying the distribution of the largest voids in the universe and comparing them to simulations, astronomers have confirmed that about 70% of the universe's energy density must be dark energy, a result that matches measurements of the cosmic microwave background. Voids are, in a sense, the perfect laboratories for studying dark energy because they are simple. No complicated galaxy dynamics, just pure expansion. But not all voids are created equal. Some exist within the dense walls of the cosmic web, carved out by the gravitational pull of merging galaxy clusters. Others are the primordial voids from inflation, sitting in the low-density backwaters. The largest known void by volume is the one we happen to live in, the KBC void, named after its discoverers, Keenan, Barger, and Cowie. This void is roughly 2 billion light-years in diameter, and it contains the Milky Way, the Local Group, and even a large part of the Laniakea supercluster of galaxies. Wait, does that mean we live inside a void? Yes. The KBC void is defined by a lower-than-average density of galaxies compared to the surrounding universe. Our home is in a relatively sparse region, about 20% less dense than the cosmic average. That might not sound like much, but on the scale of billions of light-years, it is significant. We are not in the center of the void, but we are closer to the center than to the edge. This position has direct implications for our observations. Because the surrounding galactic walls are denser, they exert a gravitational pull on us, drawing us through the void toward the filaments. This motion, known as the bulk flow, interferes with our measurements of the Hubble constant, the rate at which the universe is expanding. In fact, it may explain why the Hubble constant measured from nearby galaxies differs from the value derived from the cosmic microwave background. The KBC void is like living in a rural town far from the bustling cities of the cosmic web. The night sky is a little darker, the galaxies a little sparser, but we are still part of the grand structure. Now, imagine if we were not in a mild void like the KBC, but instead inside something like the Bootes void. What would that mean for us? First, the night sky would be devastatingly empty. Our own galaxy would still shine, but beyond it, there would be no Andromeda, no Triangulum, no nearby dwarf galaxies. The nearest galaxy might be hundreds of millions of light-years away. When you look up, you would see only the stars of the Milky Way. And then, after decades of searching with powerful telescopes, you might detect a few faint smudges, those 60 isolated galaxies scattered through the void. But they would be so far that they would appear as tiny, unresolved blobs, not the magnificent spirals we see from Earth. Your astronomers would have to work much harder to discover that the universe extends beyond your own island of stars. Your telescopes would not reveal the cosmic web until much later in your technological history. And because those distant galaxies are moving away from you due to cosmic expansion, the light from them would be severely redshifted, making them even harder to detect. In fact, if you were inside a truly deep void, the expansion of the universe might cause the galaxies on the void's boundaries to recede so fast that they would appear to be moving away faster than the speed of light in terms of recession velocity, and eventually they would vanish beyond your cosmic horizon. Generations of astronomers would live and die before any definitive proof of other galaxies emerged. There is another profound consequence of living inside a void. The cosmic microwave background would look different. The CMB is the afterglow of the Big Bang, a uniform bath of microwave radiation that fills the entire universe. Its temperature varies by a few microkelvins across the sky, revealing the seeds of structure. But if you were inside a large void, the CMB would appear slightly colder in that direction because the photons from the early universe would lose energy as they climbed out of the gravitational well of the void. Or rather, they would gain energy as they fell into the void from the denser surrounding regions. Actually, the integrated Sachs-Wolf effect describes how photons passing through a void or a supervoid get slightly blue-shifted or red-shifted depending on the evolution of the void. In a universe with dark energy, a void that is still growing imprints a cold spot on the CMB. This brings us to one of the most intriguing mysteries of modern cosmology, the CMB cold spot. In the early 2000s, the Wilkinson Microwave Anisotropy Probe, WMAP, mapped the cosmic microwave background with unprecedented precision. It revealed a large, unusually cold region in the sky, near the constellation Eridanus. The temperature difference between this spot and the surrounding warmer ring is about 70 microkelvins, much larger than the average fluctuation of about 20 microkelvins. In some places, variations can reach 140 microkelvins, but the cold spot stood out because of its sheer size and the sharp contrast with its surroundings. Initial speculation ran wild. Some fringe theories suggested it was a bruise from a collision with another universe, or a region where the laws of physics were different. But the scientific community demanded evidence. In 2013, the Planck satellite, with even greater sensitivity and resolution, confirmed the cold spot's existence, ruling out the possibility of a WMAP instrumental error. The cold spot is real. So, what causes it? One of the most compelling explanations is that the cold spot is the imprint of an enormous supervoid, a region of space so large and so empty that its gravitational influence stretches the light of the CMB, stealing a tiny amount of energy from the photons as they pass through. This is called the integrated Sachs-Wolf effect, or ISW effect. In a universe dominated by dark energy, large voids grow over time, and photons climbing out of these voids lose energy, appearing colder. To produce the observed cold spot, the hypothetical supervoid would need to be at least 500 million light-years in diameter, and possibly as large as 1 billion light-years, dwarfing even the Bootes void. It would be the largest void ever found, and it would lie about 6 to 10 billion light-years away in the direction of the cold spot. Subsequent studies have looked for direct evidence of such a supervoid by surveying galaxy counts in that region. Some surveys reported a significant underdensity of galaxies, consistent with a huge void. Others found a less pronounced deficit. The results have been mixed, but the supervoid hypothesis remains viable. It is not supernatural. It is a natural consequence of large-scale structure and the influence of dark energy. The cold spot is not a crack in the cosmic egg. It is a window into the enormous empties that pepper the universe. Now, let us delve deeper into the concept of time dilation when traveling across void distances. The distances we are talking about are almost incomprehensible. A typical void is 30 million light-years across. Even at the speed of light, traveling from one side to the other would take 30 million years. But our spacecraft cannot reach the speed of light. If we could somehow accelerate to 99.9% of the speed of light, time dilation would work in our favor, or against us, depending on perspective. From the point of view of an observer on Earth, the journey would take slightly more than 30 million years. But for the astronauts on board, due to relativistic time dilation, the trip would last only a fraction of that time. At 99.9% of C, the time dilation factor is about 22, so the crew would experience about 1.36 million years of subjective time to cross that 30 million light-year void. That is still an incomprehensible duration, but it is shorter than the external time. If we could push to 99.999% of C, the dilation factor jumps to about 224, and the subjective time drops to about 134,000 years, still far beyond a human lifetime. But if we consider an even larger void, like the Bootes void at 300 million light-years, the numbers become even more staggering. To cross that distance at 99.999% of C, the crew would experience over 1 million years. The point is that even with extreme time dilation, the sheer scale of these voids makes interstellar, let alone intergalactic, travel virtually impossible for biological beings. Time dilation is not a magic bypass. It merely compresses an already astronomical timescale into a still astronomical one. But time dilation also affects how we observe galaxies inside voids. Light from those 60 isolated galaxies in the Bootes void has taken hundreds of millions of years to reach us. We see them as they were hundreds of millions of years ago. Because the void is expanding, the light is redshifted, and the redshift tells us their distance and the expansion rate. Interestingly, if a civilization evolved inside one of those void galaxies, they would observe a very different universe. The cosmic expansion would appear to be faster because the void itself expands more rapidly than the average. Their measurement of the Hubble constant would be biased high. They might conclude that the universe is younger than it actually is, and because there are so few galaxies to study, their cosmology would be based on very sparse data. It would take them much longer to figure out the existence of dark energy. They might even develop a different theory of gravity to explain the apparent emptiness around them. This is a humbling thought. Our own understanding of the universe is shaped by the fact that we live in a moderately dense region surrounded by a rich web of galaxies. If we lived in a deep void, our cosmic perspective would be radically different. Now, let us consider a more extreme scenario. What if Earth itself were not just inside a mild void like the KBC, but deep inside a supervoid with a diameter of, say, 2 billion light-years? The implications for life would be profound. First, the density of matter around us would be so low that the formation of structures like our solar system might have been impossible. Voids are born from the same initial fluctuations that created galaxies, but in a void, the density is too low for gas clouds to collapse efficiently into stars and planets. The Bootes void, for instance, contains only 60 galaxies, but those galaxies did form. So small pockets of higher density do exist inside voids, and they can host planets. However, those galaxies are old and isolated. If Earth were in such a galaxy, the night sky would be almost completely devoid of other galaxies. That would have consequences for the history of science. Without the Andromeda galaxy visible to the naked eye, something that is easily seen from dark locations on Earth, early astronomers would have no evidence that the universe extended beyond the Milky Way. The Copernican revolution might be delayed by centuries. The concept of an expanding universe might never be discovered until far later, because there would be no nearby galaxies to measure redshifts. The cosmic microwave background would still be detectable, But its dipole, the slight temperature difference caused by our motion through the universe, would also be different because our motion relative to the CMB would be influenced by the large-scale flows around the void. It is entirely possible that a civilization inside a deep void would never develop a theory of the Big Bang until they had built telescopes capable of detecting extremely faint, distant galaxies on the void's boundary. Science would progress in a different direction, but perhaps the most significant implication of living inside a void is the effect on our measurements of the expansion rate of the universe. As mentioned, the KBC void biases our local measurement of the Hubble constant. This tension, known as the Hubble constant problem or Hubble tension, is one of the hottest topics in cosmology. The value measured from nearby supernovae and Cepheid variables is about 73 kilometers per second per megaparsec, while the value inferred from the cosmic microwave background is about 67. The difference is small, but statistically significant, and it may be due to our position in a void. If we lived in a deeper void, the discrepancy would be even larger. In fact, some cosmologists have proposed that the Hubble tension might be entirely explained by a local void that is larger and emptier than the KBC. If that is the case, then the universe's true expansion rate is the one from the CMB, and our local measurement is biased. This is a beautiful example of how our cosmic address, even on the largest scales, affects our view of reality. Now, let us turn to the future. Voids are not static. They grow as the universe expands. Over the next tens of billions of years, the voids will become even larger and emptier. The galaxies within the walls and filaments will continue to merge, forming ever more massive clusters, but the voids between them will stretch, and the galaxies inside voids, which are few and far between, will become increasingly isolated. In the far future, after trillions of years, the accelerating expansion will have pushed everything beyond our local gravitationally bound group out of sight. Each galaxy will sit alone in its own Hubble volume, surrounded by a void that stretches to the cosmic horizon. The universe will become a collection of isolated islands of stars, each one at the center of its own immense void. Eventually, even those stars will burn out, and matter will decay into radiation and black holes, which will then evaporate. The universe will approach a state of maximum entropy, a cold, dark, uniform exchange. At that point, the distinction between void and structure will vanish. The entire cosmos will be one colossal void, as empty as the spaces between galaxies are today. But for now, voids remain one of the most fascinating and underappreciated components of the universe. They are not just empty, they are active participants in cosmic evolution. They shape the motion of galaxies. They imprint on the cosmic microwave background. They test our theories of dark energy, and they remind us that the universe is not a uniform soup, but a complex, sponge-like network of matter and void. The next time you look up at a clear night sky and see the Milky Way stretching overhead, consider that the darkness between the stars is not just the absence of light. It is a gateway to the vast emptiness that fills most of the universe. And somewhere out there, in one of those million light-year wide voids, there may be a lone galaxy with a planet where a civilization is gazing at a sky that holds only a single smudge of light, their own galaxy, and wondering if they are alone. They are. In the most profound sense, we all live in a void. It is just a matter of scale. But what does the history of void discovery tell us about how we came to understand these colossal emptinesses? Let us travel back to the 1970s, a decade when astronomy was undergoing a quiet revolution. Redshift surveys, the systematic measurement of how fast galaxies are moving away from us, were beginning to reveal the universe in 3 dimensions for the first time. Before then, our picture of the cosmos was essentially a flat map. We knew where galaxies were on the sky, but we had no idea of their depth. The first hints of voids emerged when astronomers noticed that certain patches of sky seemed to contain far fewer galaxies than expected, even after accounting for obscuring dust. In 1977, a team led by Stephen Gregory and Laird Thompson studied the region around the Coma Cluster, one of the richest galaxy clusters in the nearby universe. They found that the density of galaxies in front of the cluster dropped dramatically, as if there were a bubble of emptiness stretching for tens of millions of light-years. This was one of the first tentative identifications of a void. But the real breakthrough came in 1981, when a team of astronomers using the Kitt Peak National Observatory's 4-meter telescope announced the discovery of an enormous void in the direction of the constellation Bootes. The Bootes void, as it became known, was estimated to be between 250 and 330 million light-years in diameter. At the time, this was shocking. Standard models of galaxy formation predicted that voids of that size should not exist. There simply hadn't been enough time since the Big Bang for gravity to empty out such a vast region. The discoverers, led by Robert Kirshner, initially called it a great hole and speculated that it might be a statistical fluke. But subsequent surveys confirmed it. The Bootes void was real, and it contained only a handful of galaxies, perhaps 60, where thousands were expected. The void's existence forced cosmologists to rethink how large-scale structure forms. It was a clue that the universe's initial density fluctuations were far more extreme than previously imagined, and that voids could grow to enormous sizes through the interplay of dark matter and dark energy. The Bootes void also earned a nickname that stuck, the Great Nothing, and it became a focal point for philosophical speculation. What would it be like to live inside such a void? As we discussed earlier, if humanity had evolved in one of those 60 isolated galaxies, our view of the cosmos would be radically impoverished. But let us delve deeper into that scenario. Imagine a civilization on a planet orbiting a star in the Bootes void. Their night sky would be almost completely black. The Milky Way, their own galaxy, would appear as a faint, elongated smudge, but there would be no Andromeda, no Magellanic Clouds, no recognizable constellations of external galaxies. For thousands of years, their astronomers would believe that their galaxy was the entire universe. They might develop a geocentric or heliocentric model, but they would have no evidence that other galaxies exist. The concept of an expanding universe would be impossible to formulate because there would be no distant objects to show redshift. Their cosmic microwave background would still be detectable, but it would appear incredibly uniform. The anisotropies caused by large-scale structure would be much smaller because the void's density fluctuations are suppressed. They might conclude that the universe is static and unchanging. Only when they developed extremely sensitive telescopes capable of detecting the faint, highly redshifted light of galaxies at the void's boundary, galaxies that are hundreds of millions of light years away, would they begin to suspect that they are not alone? And even then, the redshift of those boundary galaxies would be so extreme that they might misinterpret it as a property of the galaxies themselves rather than cosmic expansion. This thought experiment is not just idle musing. It has real implications for our own cosmological biases. We live in the KBC void, a region of space about 2 billion light-years across that has a galaxy density roughly 20% lower than the cosmic average. That may not sound like much, but it is enough to cause a measurable bias in our local measurement of the Hubble constant. In fact, the KBC void was first proposed in 2013 by a team led by Ryan Keenan, and it has since been refined by other studies. The void is centered relatively close to us. We are within about 200 million light-years of its center, and it extends to include the entire Laniakea supercluster, which contains the Milky Way, the Local Group, the Virgo cluster, and many other structures. So, we are not in a deep, empty void. We are in a modest underdensity. But the effect is real. The gravity of the denser surrounding walls pulls us slightly toward them, giving our local group a peculiar velocity of about 600 kilometers per second relative to the cosmic microwave background. This peculiar velocity alters the measured redshifts of nearby galaxies, and if not accounted for, it leads to an overestimate of the local expansion rate. Hence, the Hubble tension. Measurements from supernovae and Cepheid variables give a value of around 73 mpc, while the CMB gives 67.44 mpc. The difference is about 8%, which is too large to be explained by measurement error. Some cosmologists argue that the entire tension could be resolved if our local void is larger and emptier than currently thought. In other words, the Hubble constant problem might be a signature of our position in the cosmic web. This brings us to a crucial point. Voids are not just passive empty spaces. They are active agents that shape the large-scale velocity field. Galaxies move toward the densest regions, draining the voids. Over billions of years, this flow leaves voids increasingly empty, while the walls become denser and more clustered. The process is analogous to the formation of soap bubbles. The bubbles grow as gas pushes out from the interior, leaving thin films of liquid between them. In the cosmic web, voids are the bubbles, and filaments are the films. And just as soap bubbles can merge, so too can voids. The Bootes void is thought to be the result of two smaller voids merging, leaving a nearly spherical shape and a tube of remnant galaxies at its center. This merger process is ongoing. As the universe expands, voids of all sizes continue to grow, and occasionally, when two voids expand into each other, their boundaries collapse into a single larger void. This is how the largest supervoids form. Now, let us turn to the discovery of those supervoids. In the 1990s, the Las Campanas Redshift Survey mapped 26,000 galaxies and revealed a network of voids and walls spanning hundreds of millions of light-years. Then came the Sloan Digital Sky Survey, which by the 2000s had cataloged over 1 million galaxies. This data allowed astronomers to identify voids statistically. One of the largest voids found by SDSS is the Hercules supercluster void, also known as the Great Wall Void, which lies on the edge of the Hercules supercluster. It measures about 300 million light-years across. But even that is dwarfed by the giant void, discovered in 2001 in the constellation Canes Venatici. That void is about 1.3 billion light-years in diameter, making it one of the largest known structures of any kind. And yet, it is still not the largest void by definition. The KBC void, as we said, is about 2 billion light-years in diameter, but it is not totally empty. It contains our own supercluster. So, the record for the largest truly empty void might belong to something else. In 2015, a team led by Istvan Sapudi used data from the Pan-STARRS telescope and the Wide-Field Infrared Survey Explorer to identify a possible supervoid in the direction of the CMB cold spot. They found a region with a significant deficit of galaxies, about 1.8 billion light-years across. This candidate supervoid, if confirmed, would be the largest single void ever detected, and it would be aligned almost perfectly with the cold spot. The integrated Sachs-Wolf effect from such a void could produce the observed temperature anomaly. However, subsequent surveys by the Dark Energy Survey and the VISTA telescope found a less pronounced deficit, leaving the matter unresolved. The Eridanus supervoid, as it is sometimes called, remains a tantalizing possibility. Future surveys like the Euclid telescope, launched in 2023, and the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will map hundreds of millions of galaxies across vast volumes. They will be able to confirm or refute the supervoid hypothesis by measuring the galaxy density and the gravitational lensing signal around the cold spot. But even if the cold spot is not caused by a supervoid, the search has taught us something valuable. Voids can be used as cosmic testbeds for dark energy. The integrated Sachs-Wolf effect is sensitive to the growth rate of voids, which in turn depends on the amount of dark energy in the universe. By stacking the CMB signals from thousands of known voids, astronomers have measured a subtle but statistically significant ISW effect, consistent with the standard lambda CDM model, where dark energy makes up about 70% of the energy density. We like to think we know our place in the universe. We've mapped the stars, calculated the age of everything, and built models that explain galaxies and black holes with staggering precision. But every now and then, the universe reminds us just how little we actually understand. And one of those reminders is a quiet, unsettling realization: we might be living in a bubble. Not a metaphorical bubble of ignorance, but an actual physical void in the fabric of space itself. A region so vast and so empty that it challenges some of the most fundamental assumptions in cosmology. This is the story of the KBC void, a cosmic desert 2 billion light-years across, and why its existence could rewrite everything we thought we knew about the universe, about the expansion of space, and even about the search for extraterrestrial life. Let's start with the scale of things. You've probably heard the numbers before. Our Milky Way galaxy contains somewhere between 100 and 400 billion stars. That's a number so large it's almost meaningless. To try to grasp it, imagine if every one of those stars had at least one planet. That would mean hundreds of billions of worlds just in our own galactic neighborhood. Now multiply that by the estimated 2 trillion galaxies in the observable universe. The total number of planets out there is almost incomprehensible. Some estimates suggest there are more stars in the universe than grains of sand on every beach on Earth. And if even a tiny fraction of those planets are in the habitable zone of their stars, the number of worlds that could support life becomes enormous. So, where is everybody? This is the Fermi paradox in a nutshell. The universe should be teeming with life, or at least with technological civilizations sending signals across the cosmos. But we have heard nothing. No definitive alien broadcasts, no laser pulses, no Dyson spheres. The sky is silent. For decades, scientists have proposed countless explanations. Intelligent life destroys itself. Civilizations are too far apart. Or maybe we are alone after all. But there is another possibility, one that has gained traction only in the last decade. What if the reason we haven't found anyone is not because they don't exist, but because we happen to live in the cosmic equivalent of a remote village far off the galactic highway? What if we are inside a void so large and so sparsely populated that other civilizations are simply too far away to notice us, and we are too far from them to hear anything at all? That idea might sound like science fiction, but it is grounded in real astronomical observations. In 2013, a team of researchers, led by Ryan Keenan, Amy Barger, and Lennox Cowie, published a paper with a startling conclusion. By analyzing the distribution of galaxies in the nearby universe, they found evidence that our Milky Way is located near the center of an enormous underdense region, a void. And not just any void. This one, now known as the KBC void, named after Keenan, Barger, and Cowie, is about 7 times larger than typical cosmic voids. It stretches approximately 2 billion light-years from end to end. That is so big that if you were to travel at the speed of light from one side to the other, it would take 2 billion years. To put it in perspective, the entire observable universe is about 93 billion light-years across. This void occupies a significant fraction of our local cosmic neighborhood. Before we dive deeper, let's clarify exactly what we mean by a void. In astronomy, voids are regions of space where the density of matter is much lower than average. The universe, on large scales, is not a uniform soup of galaxies. Instead, it has a structure that looks something like a cosmic foam. There are dense clusters of galaxies connected by filaments, and in between those filaments are vast, empty spaces called voids. A typical void might be a few 100 million light-years across and contain only a handful of galaxies, or sometimes none at all. The KBC void, however, is not typical. It is a supervoid, a region where the galaxy count is about 20% lower than the cosmic average. That might not sound dramatic, but it is statistically significant. Within this void, there are far fewer galaxies and therefore far fewer stars than in the regions outside. And because we are near its center, our view of the cosmos is filtered through this local emptiness. Now, you might have heard conflicting information about the Milky Way's location. Some sources say we are in a void. Others say we are in a local group of galaxies that is part of a larger supercluster. So, which is it? Let's untangle this. The Milky Way is part of the local group, which includes Andromeda and about 80 other small galaxies. The local group is, in turn, part of the Virgo supercluster, a much larger structure containing thousands of galaxies. But even the Virgo supercluster is embedded within an even larger structure called the Laniakea supercluster. So we are certainly not in an empty void in the sense that there are no galaxies around us. In fact, our local environment is quite dense compared to the deep voids far away. However, when scientists look at the distribution of galaxies on scales of hundreds of millions to billions of light-years, they find that our region is underdense compared to the average density of the universe as a whole. It's like living in a small town in the middle of a vast desert. The town itself is not empty, but the region around it is far less populated than the fertile plains elsewhere. So, the KBC void does not mean we are alone in our immediate neighborhood. It means that on very large scales, we are situated in a region that is sparser than the cosmic norm. This discovery was met with considerable skepticism at first. The standard model of cosmology, known as LCDM, lambda cold dark matter, is built on a cornerstone called the cosmological principle. This principle states that the universe is homogeneous and isotropic on large scales, meaning that matter is distributed evenly and looks the same in every direction. The existence of a void as large and as deep as the KBC void seems to violate that principle. If the universe is truly homogeneous, how can there be a region 2 billion light-years across with a significantly lower density? Cosmological simulations based on LCDM, such as the Millennium simulation or the MXXL simulation, suggest that structures like the KBC void should be extremely rare. In fact, the probability of such a void forming within the standard model is less than 1%. That immediately raises red flags. Either our observations are wrong, or our model is missing something. But as more data poured in from galaxy redshift surveys that measure the distances and motions of thousands of galaxies, the evidence for the void became harder to dismiss. The KBC void is not just a statistical fluke. It is supported by multiple independent studies. In 2017, a team including Ryan Keenan published an updated analysis confirming the underdensity out to a distance of about 300 megaparsecs, or roughly 1 billion light-years. They found that the matter density in that volume is about 20% lower than the cosmic average. And crucially, this underdensity is not uniform in all directions. It has a structure that influences the apparent motion of galaxies, a phenomenon known as the bulk flow. Galaxies inside the void are being pulled toward the denser regions outside, creating a velocity field that we can measure. This brings us to one of the most exciting implications of the KBC void. It may offer a solution to the Hubble tension. The Hubble tension is arguably the biggest crisis in modern cosmology. To understand it, we need to talk about the expansion of the universe. The universe has been expanding since the Big Bang, and the rate of that expansion is given by a number called the Hubble constant. Think of it as a cosmic speed limit. For every megaparsec, about 3.26 million light-years, farther away a galaxy is, it moves away from us faster by about 70 kilometers per second. But here's the problem. There are two different ways to measure HO, and they give different answers. The first method uses observations of the early universe. By studying the cosmic microwave background, the afterglow of the Big Bang, scientists can infer the conditions of the universe about 380,000 years after its birth. Using the standard LCDM model, they can then extrapolate forward to predict what the expansion rate should be today. This method gives a value of about 67.4 kilometers per second per megaparsec. The second method uses direct observations of nearby galaxies. Astronomers measure distances using standard candles like Cepheid variable stars and Type Ia supernovae, and then measure how fast those galaxies are receding from us. This method gives a value of about 73.0 kilometers per second per megaparsec. The difference is about 8%, and it is statistically significant. It cannot be explained by measurement errors alone. This discrepancy is the Hubble tension. It suggests that either our model of the early universe is wrong, or our understanding of the local universe is incomplete. And that's where the KBC void comes in. If we are living inside a large underdense region, then the expansion rate we measure locally might not be the true cosmic expansion rate. Here's why. Inside a void, there is less matter, so the gravitational pull is weaker. But the surrounding denser regions exert a stronger gravitational attraction, pulling matter outward. This creates an extra apparent motion, making it look like galaxies are moving away from us faster than they actually are. In other words, the void fools us into thinking the expansion is faster in our neighborhood. When scientists model the gravitational effect of the KBC void, they find that the local expansion rate measured from nearby galaxies could be inflated by about 10% compared to the true global expansion rate. That is almost exactly the size of the Hubble tension. So the Hubble tension might not be a sign of new physics like modified gravity or exotic dark energy. It could be a simple geographic effect. We happen to live in a place that skews our measurements. This is a Occam's razor solution that many cosmologists find appealing because it doesn't require us to throw out the entire LCDM model. However, this explanation is not without its own problems. For the void to have such a strong effect, it must be quite deep and quite large. And as we already mentioned, standard LCDM simulations struggle to produce voids of this size and depth. So, the void explanation for the Hubble tension actually compounds the original problem. We now have to explain why such a void exists in the first place. This has led some researchers to consider alternative theories of gravity. One of the most prominent is modified Newtonian dynamics, or MOND. MOND was originally proposed to explain the rotation curves of galaxies without invoking dark matter. It suggests that at very low accelerations, like those found at the edges of galaxies, gravity behaves differently than Newton predicted. When applied to cosmological scales, MOND predicts that structure formation happens faster than in LCDM. In a MOND universe, large voids like the KBC void are much more likely to form because gravity is stronger in low-density regions, causing matter to clump together more efficiently. So, the existence of the KBC void could be seen as evidence in favor of MOND. But MOND also has its own difficulties. It cannot fully explain the cosmic microwave background or the large-scale clustering of galaxies as seen in surveys like the Sloan Digital Sky Survey. The debate between LCDM and MOND continues, and the KBC void sits right in the middle of it. Now, let's turn to the Fermi paradox. How does living in a void affect our chances of encountering extraterrestrial intelligence? The classic argument is that if the universe is teeming with civilizations, we should see some evidence of them, whether it's radio signals, probes, or megastructures. But if our galaxy is situated in a vast underdense region, then we are effectively isolated. The number of galaxies within the KBC void is lower than average, which means fewer stars and fewer potential habitable planets. Even if intelligent life is common in the universe, it might be concentrated in denser regions like the Virgo supercluster or the Great Attractor region. Our local group of galaxies might be a backwater. The distances to the nearest galaxies outside the void are enormous, on the order of hundreds of millions of light years. Any signals from those civilizations would take hundreds of millions of years to reach us, and we have only been listening for a few decades. Moreover, there is an even more speculative idea. Civilizations in denser regions might avoid expanding into voids because they are resource poor, or they might simply be unaware of our existence. The anthropic principle also plays a role here. Some have argued that we should not be surprised to find ourselves in a void, because voids provide a relatively safe environment for life to evolve. In denser regions, galaxies collide more often, supernovae are more frequent, and radiation levels are higher. A void offers a more stable, quiet corner of the universe, where life can emerge without being constantly disrupted by cosmic violence. So, our location in the KBC void might actually be a necessary condition for our existence. This is a version of the anthropic selection idea. We observe a low-density region because only in such a region could observers like us arise. But we need to be careful. The anthropic principle is often criticized as a philosophical cop-out because it can explain almost anything by saying, if things were different, we wouldn't be here to observe them. Nevertheless, when combined with the empirical evidence for the KBC void, it offers a coherent narrative. We are in a bubble of relative emptiness, which explains both the Hubble tension and the silence of the cosmos. This does not mean the void is definitely the answer. Scientists are still gathering data. New surveys like the Dark Energy Spectroscopic Instrument, DESI, and the Euclid mission are mapping the distribution of galaxies with unprecedented precision. In the next few years, we will get a clearer picture of whether the KBC void is a true anomaly or just an artifact of biased samples. One important caveat: not all astronomers agree that the Milky Way is inside the KBC void. Some argue that the observed underdensity is a result of selection effects. Maybe we are just not seeing all the galaxies in that direction because of dust or other observational biases. Others point out that the evidence for the void relies heavily on the Tully-Fisher relation, which is not perfectly calibrated. There is also a rival idea called the dark flow hypothesis, which suggests that the bulk motion of galaxies is caused by the gravitational pull of structures beyond the observable universe, not by a local void. So, the debate is far from settled. The KBC void is a hypothesis, not a proven fact, but it is a hypothesis with strong observational support and profound implications. Let's step back for a moment and think about what it means to live in a cosmic void. The universe is unimaginably vast, and we are just a tiny speck on a planet orbiting an ordinary star in an ordinary galaxy. But if the KBC void is real, then our galaxy is even more ordinary than we thought. It is situated in a region that is emptier than average. That emptiness might be the reason we feel so alone. It might also be the reason we measure the universe to be expanding faster than it actually is. It might even be the reason our theories of gravity and dark matter seem to work so well locally but break down at larger scales. Ultimately, the KBC void is a reminder that our perspective is limited. We are embedded in the universe, not outside it, and our observations are inevitably biased by our location. As we refine our maps of the cosmos, we may discover that we are not at the center of anything special, except perhaps the center of a vast, quiet desert. And that might be the most profound discovery of all. The silence of the universe is not a sign that we are alone, but a sign that we are in a very quiet neighborhood. So the next time you look up at the night sky, think about the void. Those stars you see are mostly in our own galaxy, but beyond them, in every direction, lies an expanse so empty that it stretches for billions of light years. We are surrounded by emptiness, and that emptiness shapes everything we see, every measurement we make, and every search for other minds. It may be the most important thing about our cosmic address. We don't yet know if the KBC void will stand the test of time, it's a confirmed feature of the universe. But the story of its discovery, the controversy it sparked, and the solutions it offers show that science is alive and messy. The Hubble tension remains unresolved. The Fermi paradox continues to haunt us, and the debate between LCDM and Mundi rages on. But one thing is clear, the universe is not as simple as we once thought, and that is exactly what makes it so fascinating. Now, if you've enjoyed this journey through the cosmic void, consider subscribing, because the universe is full of mysteries, and we've only scratched the surface. From dark energy to the great attractor, from cosmic voids to multiverse theories, there's always more to explore. So stay curious and keep looking up. Because even if we are living in a bubble, it's a bubble that contains everything we know and love. And that's pretty amazing. Thanks for watching. And if you want to dive deeper into the science of voids and the Hubble tension, check out the links in the description for further reading. I'll see you in the next video. Before we wrap up, let's revisit what the KBC void actually means for our everyday understanding of the cosmos. We often think of the universe as a vast, evenly sprinkled collection of galaxies, like raisins in a perfectly mixed dough. But the KBC void suggests that the dough has giant bubbles, and we happen to be inside one. That's a humbling thought. It means our local patch of the universe is not representative of the whole, and that has consequences not just for cosmology, but for how we interpret every astronomical observation we make. Take, for example, the measurement of dark energy. The standard model of cosmology includes a mysterious force called dark energy that is supposedly causing the expansion of the universe to accelerate. That conclusion comes from observations of distant Type Ia supernovae in the 1990s, which won a Nobel Prize. But if we are inside a void, the apparent acceleration might be partly an illusion. The void could mimic the effects of dark energy on the expansion history. Some researchers have even proposed that we don't need dark energy at all if the void is deep enough and we are located close to its center. This is a radical idea, but it has been explored in papers using the timescape model, which argues that the universe expands at different rates in voids and in dense regions, and that our perception of acceleration is a result of averaging over these inhomogeneities. While the timescape model is not widely accepted, it shows that the void hypothesis forces us to question some of our most cherished assumptions. The KBC void also has implications for the cosmic microwave background. The CMB is a snapshot of the universe at 380,000 years old, and it is remarkably uniform. But if we are inside a large void, that void would leave an imprint on the CMB via the integrated Sachs-Wolf effect. As photons travel through the void, they gain energy when entering and lose energy when exiting. But due to the gravitational potential changing over time because of the expansion, there is a net shift. For a void as large as KBC, this effect should be detectable. And indeed, there are hints of a cold spot in the CMB in the direction of the Eridanus supervoid, which is a smaller void. The KBC void might contribute to a larger-scale anomaly. So far, the data is inconclusive, but future CMB surveys like the Simons Observatory could help pin this down. Now, let's address the elephant in the room, the conflicting information about the Milky Way's location. You might have heard that we are on the outskirts of the Virgo supercluster, or that we are near the center of the Laniakea supercluster. These are different scales. The KBC void is a much larger structure, billions of light-years across, while the Laniakea supercluster is about 500 million light-years across. So, it's perfectly possible for the Milky Way to be both in a supercluster, a dense region on intermediate scales, and in a giant void, an under-dense region on larger scales. Think of it like a foam. There are dense filaments and walls, but on the largest scales, even those filaments are part of a bigger bubble. Our galaxy sits in a relatively dense local filament, but that filament is embedded in a vast, underdense region. That is precisely what the KBC void describes, a lower-than-average density on scales of hundreds of megaparsecs, even though our immediate neighborhood is normal. One of the most cited studies on the KBC void is the 2017 paper by Keenan, Barger, and Cowie. They used a sample of galaxies from the 2-micron all-sky survey, 2MASS, and the 2MASS redshift survey, 2MRS. They found that the number density of galaxies within 300 mpz is about 20% lower than the mean. They also noted that this underdensity is not isotropic. It is more pronounced in certain directions, which is consistent with a void that is slightly elongated. Subsequent work by other teams, using data from the Sloan Digital Sky Survey and the 60th Galaxy Survey, has generally supported this finding, although some studies have found a smaller underdensity of around 10 to 15%. The debate is ongoing, but the key point is that the existence of a significant underdensity in the local universe is now widely accepted. The question is its exact size and depth, and that brings us to the scientific standing of the KBC void. It is not yet a settled fact. Some cosmologists argue that the observed underdensity could be a selection effect. Maybe we are missing galaxies because of dust extinction, or because low-luminosity galaxies are harder to detect. Others point to the fact that the peculiar velocity of the local group, our galaxy and its neighbors, relative to the CMB, is about 600 kilometers, which is unusually large. If we are in a void, we would expect a large bulk flow toward the denser regions, and indeed, the observed peculiar velocity is consistent with that picture. But alternative explanations exist, such as the pull from a massive structure like the Shapley supercluster, or even the Great Attractor. The KBC void is just one piece of a complex puzzle. Perhaps the most exciting aspect of the KBC void is how it connects different mysteries. The Hubble tension, the Fermi paradox, the large-scale bulk flows, the abundance of voids in simulations, all these threads come together if we accept that we live in an unusually empty region. This kind of cross-disciplinary synthesis is rare in science, and it makes the void hypothesis very attractive. But it also means that if the void is disproven, we will lose a unifying explanation and be left with multiple separate puzzles. So, what does the future hold? Over the next decade, surveys like DESI will map the positions of tens of millions of galaxies, giving us a three-dimensional map of the local universe with unprecedented detail. If the KBC void is real, we should see a clear signature, a spherical or ellipsoidal region where the galaxy density is low, surrounded by a denser shell. We should also see a coherent flow of galaxies away from the void center. These predictions can be tested. On the theoretical side, cosmologists are running new simulations with alternative gravity models to see if they can reproduce such a void without violating the CMB constraints. If MOND or other modified gravity theories can do it, then the existence of the KBC void becomes a strong argument for revising our standard model. But let's not get ahead of ourselves. The universe has a way of surprising us. Perhaps the KBC void will turn out to be a statistical fluctuation after all, a rare but not impossible event in LCDM. Or perhaps it will be confirmed, and we will have to accept that we live in a very special place. Not special in the sense of being privileged, but special in the sense of being peculiar. That peculiarity could explain why we feel so isolated and why our measurements of the expansion rate are off. I want to leave you with a final thought. The idea that we are inside a cosmic void is not just a scientific curiosity, it's a profound shift in perspective. For centuries, humans believed they were at the center of the universe. Then Copernicus moved us to a planet orbiting the sun. Then we learned the sun is just one star among billions in the Milky Way. Then we discovered the Milky Way is just one galaxy among billions. Now, we are learning that even our galaxy's position is not average. It's in a desolate region, a cosmic backwater. That's a humbling progression. But it also gives us a unique vantage point. From inside the void, we can see the rest of the universe without the clutter of too many galaxies in our way. It's like being in a dark room with a clear view of the light outside. So the next time you feel small and insignificant, remember, you are not just a speck on a pale blue dot. You are a speck inside a bubble of emptiness that stretches for billions of light years, and from that bubble, you are trying to understand the whole cosmos. That's a remarkable thing. Keep asking questions, keep looking up, and maybe, just maybe, the void holds the answers we've been searching for all along. Thank you for watching. If you enjoyed this deep dive into the KBC void and its implications, please like and subscribe. It really helps the channel. And let me know in the comments. Do you think we are alone because we are in a void? Or is there another explanation for the great silence? I'll read your thoughts and discuss them in a future video. Until then, stay curious and keep exploring the cosmos from our quiet little corner of the universe. Until then, stay curious and keep exploring the cosmos from our quiet little corner of the universe. But let's push a little further into what this void means for our understanding of life itself. You see, if we are indeed inside a cosmic void, a region with fewer galaxies, fewer stars, fewer planets, then the sheer scarcity of habitable worlds within our immediate vicinity becomes a kind of selection filter. It's not just that we are far from other civilizations because the void is empty. It's that the very conditions that allowed intelligent life to emerge here might be tied to the void's existence. Some researchers have proposed that voids, being less dense, experience weaker tidal forces and fewer violent events like galaxy mergers or supernova blasts. That relative calm could provide a stable environment for planetary systems to evolve over billions of years without repeated cosmic catastrophes. In other words, the void might be a cradle for life, not a desert. Think about that. We may be living in a quiet, protected bubble, an oasis of stability in a universe that is otherwise chaotic and crowded with destructive events. That flips the Fermi paradox on its head. Maybe it's not that we are isolated, maybe we are privileged. The void gave us the time and space to develop, while civilizations in denser regions might get wiped out by gamma-ray bursts or gravitational disturbances before they ever reach the stage of spacefaring technology. If that's true, then the silence of the cosmos is not a sign of loneliness, but a sign of our good fortune. We are the lucky ones, sitting in a cosmic sanctuary. Now, there is a darker twist to this idea. If the void is indeed protective, then stepping outside the void might be dangerous. As we send probes and signals farther into the universe, we are essentially shouting into a dense forest full of predators. The void's very emptiness might be why we haven't heard from anyone else. They might have learned to stay quiet in order to survive. That's a sobering thought, and it adds a whole new dimension to the search for extraterrestrial intelligence. Maybe the reason we haven't found anyone is that everyone who could broadcast has already been silenced by the very forces that our void shields us from. It's a hypothesis that pushes us to reconsider our own future. Should we be broadcasting our presence at all? Are we inviting trouble by sending messages into the denser regions beyond our local hole? These are questions that science fiction has explored for decades, but now cosmology gives them a concrete foundation. Our location inside the KBC void might be both a blessing and a curse. It allows us to exist, but it also blinds us to the dangers lurking just beyond our horizon. Let's also consider how the void affects our understanding of the universe's large-scale structure. The cosmic web, the network of filaments and voids that makes up the universe on its grandest scales, is a direct consequence of the initial density fluctuations after the Big Bang. In the Standard Model, small ripples grew over time under gravity to form the clumpy distribution we see today. The voids are the underdense regions that have been drained of matter by the gravitational pull of the filaments. But the KBC void is so large, about 2 billion light-years across, that it challenges the typical size distribution predicted by simulations. It's like finding a room in your house that is 10 times bigger than any other room, with almost no furniture inside. That anomaly suggests that the initial conditions in our local patch of the universe might have been different. Perhaps we are sitting in a region that experienced a rare extreme fluctuation, one that is statistically improbable but not impossible. And that improbability has deep implications for the Copernican principle, which states that our position in the universe is not special. If the KBC void is real, and we are near its center, then our position is actually quite special. It would mean that the universe has a privileged observer, us, in a place that is far from average. That would be a revolution in cosmology comparable to the shift from a geocentric to a heliocentric model. We would no longer be just a typical observer. We would be an atypical observer, and that would force us to reconsider every statistical inference we make about the universe from our local sample. And here is another layer. If we are in such a large void, then the expansion rate we measure locally is not the true global expansion rate. As we discussed, the Hubble tension might be resolved by the void's gravitational effects, but that resolution comes at a cost. It means our measurements of dark energy, which rely on the assumption of homogeneity, could be fundamentally flawed. The entire edifice of modern cosmology, the lambda CDM model with its dark energy and dark matter,